This video is for topic 3.5, which is kinetic molecular theory. And the objective for this topic is to explain the relationship between the motion of particles and the macroscopic properties of gases with the kinetic molecular theory, a particulate model, and a graphical representation. So we're going to use the theory, a drawing, and a graph to explain what's going on with our gases. So let's first talk about the theory. So kinetic molecular theory says that the particles are super far apart compared to their size. So what this means is that we can ignore the volume of the individual particles. So the volume, we can assume that the volume of the container is the volume of the gas and that there isn't any other volume changes that we have to account for because the gas particles are so incredibly small. It also says that these particles move in continual, rapid, and random motion. So they're always moving, they move very fast, and the motion is completely random. The third part is that the collisions don't transfer energy. So particles are going to collide with each other, they're going to collide with the sides of the container. And when they collide, the theory says that those collisions are not going to transfer energy. So they're also called completely elastic collisions. This means that our average kinetic energy of the gas is related to the temperature. So we can use the temperature to discuss or think about the average kinetic energy of the gas particles. The graph part of this is using what's called a Maxwell-Boltzmann curve. Okay, so what this shows is the distribution of energies at a specific temperature. So remember, we're talking about average energies. So if we think about the definition for kinetic energy is 1/2 mv squared. So what we're talking about is the average speed for all gas particles. The root mean square speed, or RMS speed, is related to the molar mass. So obviously, heavy particles are going to move slower, smaller particles are going to move faster. Okay, so the smaller your molar mass, the faster your root mean squared speed. So when we're looking at this particular type of graph, we're thinking about the average. So we're looking at the distribution of all the energies at a certain temperature. And remember, we're measuring temperature in Kelvin, so there aren't any negative numbers. And to get from Kelvin to Celsius, or Celsius to Kelvin, we add 273 to our Celsius value. So Kelvin is our absolute temperature scale, which means that there are no negative numbers. Absolute zero is no motion, okay? And so when we look at a graph like this, so what this tells us is the fraction of the particles that are moving at that speed for that temperature. So if we look at our curve here, we have a curve for 300 Kelvin, and we have a curve for 1000 Kelvin. So most of our particles are going to move about the same. However, some are going to move a little faster, some are going to move a little slower, but we look at the average for the average energy, the average speed for all the gas particles. So when we draw them, I don't have any drawing examples. When we draw gas particles, we're going to think about how quickly they move, and they're going to be far apart. So we can use our theory, we can use our graphs, and we can use particle diagrams to represent how a gas might behave.